Have you ever felt overwhelmed by the endless search for clean, reliable, pre-trained models in PyTorch? If you've juggled different architectures, input sizes, and half-documented GitHub repositories, you're not alone. For years, PyTorch users have been stuck in a web of mismatched configs and incompatible checkpoints, making transfer learning a real headache. But what if there was a way to simplify all of this? Imagine a library that not only provides hundreds of pre-trained models, but also standardizes everything from pre-processing to feature extraction, so you can focus on building, not babysitting. That's where TIMM comes in, promising to turn the chaos of model management into a streamlined, plug-and-play experience. TIMM, or PyTorch Image Models, is not just another model zoo. Created by Ross Wightman, TIMM offers over 1,600 pre-trained image models with a consistent, beautifully designed API. It's the library that makes you wonder how you ever managed without it. With just one line of code, you can load any model, ResNet, EfficientNet, Vision Transformer, and more, complete with automatic pre-processing and normalization. No more hunting for the right weights or debugging data pipelines. TIMM brings a level of polish and reliability that's rare in open-source projects, making it a true sanctuary for computer vision practitioners. Despite powering thousands of production systems and being downloaded millions of times, TIMM remains a quiet giant in the computer vision world. Unlike libraries with flashy marketing, TIMM focuses on engineering excellence. It supports over 50 architecture families and is trusted by Kaggle competitors and tech companies alike. Yet many tutorials still do things the hard way, manually downloading models and writing custom pre-processing code. The reason? TIMM doesn't advertise, it just works. Its understated presence belies its massive impact on the field. Let's look at a real-world example. Diabetic retinopathy classification using the Aptos 2019 dataset. This project involved 3,662 retinal images across 5 classes, with a significant class imbalance and subtle medical features. Traditionally, setting up models for such a task meant dealing with different libraries, inconsistent APIs, and custom pre-processing for each architecture. The process was error-prone and time-consuming, especially when comparing multiple models. TIMM changed all that by offering a unified, streamlined workflow. Before TIMM, setting up multiple models for a project meant writing separate code for each architecture. You'd import ResNet from TorchVision, EfficientNet from another library, and maybe even TIMM for transformers. Each model required its own pre-processing pipeline, optimizer, and training loop. The result? Hundreds of lines of code, lots of room for mistakes, and a workflow that was anything but efficient. This approach was not only ugly and error-prone, but also discouraged experimentation with new models. With TIMM, the process is radically simplified. You can load any supported model with a single line of code, and the library automatically provides the correct pre-processing and normalization. Whether you're using ResNet, EfficientNet, or Vision Transformer, the workflow is identical. This consistency not only saves time, but also makes it easy to compare different architectures and focus on what matters, improving your results. TIMM's design philosophy is all about reducing friction and empowering rapid experimentation. One of TIMM's standout features is its discoverability. With a simple command, you can list all available models over 1,200 architectures and 1,600 pre-trained variants. Want to see all ResNet or EfficientNet models? Just filter by name. Need only pre-trained models? That's one line too. New architectures are added within weeks of their publication, ensuring you always have access to the latest research. This vast, well-organized model zoo makes TIMM a go-to resource for anyone working in computer vision. TIMM makes model comparison effortless. In the diabetic retinopathy project, 3 architectures were tested: ResNet 5.0, EfficientNet B3, and Vision Transformer Base. Each model was set up with the same code pattern, allowing for fair and direct comparison. After training, ResNet 5.0 achieved the highest accuracy, EfficientNet B3 offered the best efficiency, and ViTs showed promise with more data. This streamlined approach not only accelerates research, but also provides clear insights into each model's strengths and weaknesses. Let's look at the numbers. After 15 epochs of training with proper class weighting, ResNet 5.0 led with a quadratic weighted kappa of 0.8683, followed by EfficientNet B3 at 0.8578. and Vi base at 0.8335. Efficiency metrics showed EfficientNet B3 as the most resource-friendly, while Vi required more data and compute. The confusion matrix for ResNet 5.0 revealed excellent recall for healthy eyes, but some struggle with subtle cases mirroring real-world diagnostic challenges. These insights are invaluable for both research and deployment. TIMM isn't just about loading models. It offers powerful tools for analyzing architectures, extracting features, and customizing networks. You can inspect model internals, count parameters, and even modify classifier heads with ease. Feature extraction is straightforward, making it perfect for custom classifiers, visualization, or ensemble methods. TIMM's flexibility means you can adapt any model to your specific needs without wrestling with low-level details. How much does pre-training matter? A quick experiment compared training from scratch versus using pre-trained weights. The results were striking. ResNet 5.0 saw a 19% improvement in performance, while EfficientNet B3 jumped by 62% when using pre-trained models. This demonstrates the power of transfer learning, especially for smaller datasets or specialized tasks like medical imaging. TIMM makes leveraging these benefits as simple as flipping a switch. Even with TIMM, there are a few things to watch out for. Some models require specific input sizes, so always check the configuration. Large models can quickly exhaust your GPU memory. Use gradient checkpointing or check model size before loading. Learning rates may need adjustment depending on the architecture. And don't forget proper data augmentation. By following these best practices, you can avoid common pitfalls and get the most out of TIMM's capabilities. TIMM isn't limited to image classification. It excels at object detection, semantic segmentation, and self-supervised learning. You can use TIMM models as backbones for detection frameworks, build UNet-style architectures for segmentation, or remove classifier heads for contrastive learning. This versatility makes TIMM a valuable tool for a wide range of computer vision applications, from research to real-world deployment. TIMM integrates seamlessly with the broader PyTorch ecosystem. Whether you're using PyTorch Lightning for structured training, Hugging Face for advanced processing, or FastAI for rapid prototyping, TIMM fits right in. This compatibility ensures you can leverage the best tools in the field without worrying about interoperability issues. TIMM's design philosophy is all about making your workflow smoother and more productive. TIMM supports advanced performance optimizations like mixed precision training, model compilation, and efficient inference exports. With mixed precision, you can speed up training and reduce memory usage. PyTorch 2's model compilation brings a 20–30% speedup, and exporting models to TorchScript or ONNX makes deployment a breeze. These features ensure that TIMM models aren't just easy to use, they're also ready for production at scale. Deploying TIMM models in production brings its own set of lessons. Model selection isn't just about accuracy, latency, and resource usage matter, too. Batch size can have a big impact on performance, especially with limited GPU memory. Version pinning is critical to ensure consistent results, as model behavior can change between releases. By paying attention to these details, you can deploy TIMM models confidently in real-world applications. TIMM is evolving rapidly, with new architectures and features added regularly. Recent additions include massive models like EVA02 and efficient designs like FastVit and MaxVit. The roadmap promises even more efficient architectures, better fine-tuning recipes, and enhanced documentation. As the field of computer vision advances, TIMM remains at the forefront, ensuring you always have access to the latest and greatest tools. If you regularly build models for image data, want to compare architectures quickly, or need high-performance production quality solutions, TIMM is for you. It simplifies the learning curve, accelerates experimentation, and lets you focus on innovation rather than implementation details. Even if your needs are highly custom, TIMM likely offers more than you expect. It's the tool many wish they'd discovered sooner. In a field that moves faster than your GPU can cool down, TIMM is a calm in the chaos. It's not just about making computer vision easier, it makes it fun again. Gone are the days of scouring GitHub for half-working repos or debugging normalization issues at midnight. With TIMM, you can focus on ideas, experiment freely, and move towards the frontiers of model development. It's the unofficial standard for PyTorch vision work. and a tool that truly empowers you to do more with less hassle.